today's discussion, which is on SIL selection using exSILentia. And as always, when we start, we'd like to introduce ourselves. So first and foremost, my name is Steve Gandy. I am the VP Global Business Development for exida. Even though I've been with exida for just over 3.5 years now, I've got about 38 years industrial experience in safety and controls. I started off as a design engineer doing hardware and software design and worked for ICS in the UK for many years, designing some of the early safety systems or modules for the safety systems that we had back then for emergency shutdown, fire and gas. I'm also responsible for exida's end user business on the cybersecurity and the functional safety side. I am one of the primary instructors for the functional safety engineering course, the FSC 100, that we run regularly and have coming up in the UK a course on the 16th of November. I'm also a certified functional safety professional. I have a master's in business, and I'm a member of the ISA as well as the IET in the UK and the Association of MBAs. I have published some papers on managing risky projects, which is all about risk management, concurrent engineering, and conforming to IEC 61511 operation and maintenance requirements. So from that, we talk about exida. exida is a global company. We are based around the world, as you can see here. Here are some of the major or the main offices we have around the world. And we supply certification and services to both manufacturers and end users. Most of the manufacturers are for the certification of products to IEC 61508, although we do also provide cybersecurity certification for products. From the services point of view, we provide functional safety as well as cybersecurity and alarm management. And as you can see here, we work in many industries. We work in the automation industry, we work in the process industry, automotive and nuclear. And we've worked with the manufacturers to help them develop and support their functional safety management systems, certifying their products, and also providing tools. We have exSILentia, which is one of the leading tools for the safety industry. From the system designer's point of view, again, functional safety management and SIL verification services, plus the tools. For the end users, we can provide full safety lifecycle task support. We can help with proof tests. We can help with their functional safety management again, and any tasks that they have requiring safety or cybersecurity or alarm management. And then from the engineering contractor's point of view, we can help with competency development. As I mentioned already, I'm one of the main instructors for the FSC Functional Safety Engineering 100 course that we provide, which is effectively the replacement of our old FSC 1 and 2, which will lead to becoming a certified functional safety expert or certified functional safety professional. And also we have a new program we've introduced for functional safety practitioners. The tools we supply, I mentioned exSILentia already. That provides us with the capability of doing the full safety life cycle, which covers the analysis phase, so HAZOPs, PHAs, LOPAs, SIL selection, as we're going to talk about today, and then also through SIL verification, SRS, and proof tests, etc. The SIL stat is another tool we've created to help with actually logging performance of the safety instrumented system during its normal life in the field. So let's just recap a little bit about the standards. The primary standard, which is also known as the base standard for all industries from a safety point of view, is IEC 61508. This is what's known as the umbrella standard. And that has spawned several what are known as sector standards. For example, in the nuclear, there's IEC 61513. In machinery, it's IEC 62061. Of course, in the process industry, it's IEC 61511. And there's another one now for automotive, which is IEC 26262. And all of these are known as sector standards, which use IEC 61508 as the base for the safety requirements. So for this discussion today, we're going to focus on the process industries and in particular the IEC 61511 standard. This standard targets end users and integrators in the process industry. It covers the entire safety instrumented system lifecycle. So effectively there are three phases that we talk about. We talk about the analysis phase, where we look at the risks, we look at the hazards from the process side, and we look at what layers of protection we have in place and how much additional risk reduction we need, and therefore what is the requirement for the safety instrumented functions that would be in our safety instrumented systems from a performance point of view. The basic premise of the 61511 standard and the 61508 standard is that they are performance, not prescriptive. An example of a prescriptive requirement could be the NFPA 85, which tells you what you need to do. With a performance standard, it basically says this is what you have to do, but it doesn't tell you how to do it. So it gives you the freedom to choose technology and choose the approach that is most applicable, that obviously satisfies the amount of protection that you need. And from an end user perspective, end users are not typically certified, but the standard says that there should be at least 5 functional safety assessments performed throughout the life cycle. The only one that's mandatory is what we call Functional Safety Assessment 3, FSA 3, which effectively is the pre-startup functional safety check, where you make sure you validate to ensure that you've covered everything and that the SIS meets the SRS in all its entirety. So this is often known as the pre-startup safety check. So let's look at the life cycle, and we're going to focus, like I said, primarily on the analysis phase here, where we've done the hazard identification. In other words, what can go wrong, what potential hazards are there, and then we look at the risk analysis and SIL selection. So in other words, how bad can it be? What layers of protection do we have in place, and are these adequate? And if not, then we need to consider having additional safeguards, such as a safety instrumented system with safety instrumented functions, and therefore we would need an additional amount of risk reduction that we're looking for. That would then be fed into the safety requirements specifications, which would say, okay, here's what we need to do, and then once we've done that, we would then do a SIL verification, say, all right, now we've done that, do we meet our target? And then as we get into the operation and maintenance phase, there has to be continuous performance monitoring in order to maintain that reliability. So tolerable risk. Why do I need to specify my tolerable risk level? Well, of course, you can't determine what the required risk reduction will be without it. And there is a relationship, as we shall see, where we talk about RRF, which is risk reduction factor, is known as the unmitigated risk over the tolerable risk. Now, the unmitigated risk will be the risk that remains after you've considered all the non-safety instrumented layers of protection. So, of course, if we don't know what our tolerable risk is, how can we figure out what our risk reduction factor should be? So what if I can't tolerate any risk? Well, of course, we all live in a world where there is no such thing as zero risk. There's always something, because a tolerable risk of 0 would lead you to a required risk reduction of course, infinity, which basically means if it's that bad, don't build your plant. you're going to have too many problems. And of course, it's a simple math problem. So what is individual risk, and how do we look at this in terms of our tolerable risk? Well, there's the premise of ALARP, which is as low as reasonably practicable. Now, some of you may be familiar with this, some of you might not be familiar with this, but basically this is defined in the standard, and it defines what we accept or what we should accept in terms of the possibility of injuring or potentially killing the public and, of course, our workers. And here we see that the ALARP, or the tolerable region, falls within 10 to the minus 3 to 10 to the minus 6 per year. So somewhere in here would be a target. And again, it depends upon the company's approach and whether they're more risk averse or less risk averse. When we generally accept it, it's a lot lower than that. It's below 10 to the minus 6 per year, and of course here we're into lightning strikes. What's the probability of dying from being hit by lightning or bitten by a snake or dying in a plane crash? So of course this is where we accept it, but the ALARP region is where we would normally try and achieve the amount of risk reduction. So if we look at this in terms of, we have a process, and when we start we have our initial process risk, and what we're trying to do is we're trying to reduce that by use of our optimal risk reduction through ALARP to get to an acceptable level of residual risk, again based on the fact that we're not going to get rid of risk entirely. And so there's a number of ways we can do that. We can look at the actual process itself. We can see if we can modify that. We can look at the design of the process in the plant. We can look at our basic process control system to help us reduce the risk further. We can use alarms. And this next one is interesting because some would argue, quite rightly, that a relief such as a pressure release valve is a mitigation. In other words, we've already incurred the abnormal event, and this is helping to alleviate it. So some would say that the relief should come at the end here, because what we're looking at doing is, if having done all of this as layers of protection, non-SIS layers of protection, we now find that we still need to reduce our risk further to get to our optimal risk reduction. We need a safety instrumented system with safety instrumented functions. So how to assign a SIL? And again, I hope everybody understands that SIL is safety integrity level here. So identify how much risk reduction is needed to attain a tolerable risk. So there's a couple of ways of doing this. You can use quantitative methods, which give specific numerical targets for risk reduction. As I showed earlier, what we call the risk reduction factor. And there is, in the process industry, if you're using demand mode, in other words low demand, where your demands are going to be less frequent than once per year, then there is a direct correlation between what we call our probability of failure on demand, the average probability of failure on demand, to the risk reduction factor, which is an inverse relationship. So risk reduction factor can give us much more specific targets. The qualitative methods group these numerical targets into more broadband categories of risk reduction. So they'll get you into a SIL band. And for those of you who might not know this, the SIL 1 band is between 10, a risk reduction factor of 10 to 99. The SIL 2 is between 100 and 999. And the SIL 3 is between 1,000 and 9,999. And SIL 4 is above, but from the process point of view, the process industries, we never consider anything higher than a SIL 3. And in some cases, a lot of companies don't even want SIL 3s. They would rather go back to the drawing board and try and achieve SIL 2s. But whichever method you use, it has to be consistent. so that you can make sure you get the same results. So what are the common SIL selection methods? Well, typically there are three: the risk graph, the risk or hazard matrix, some people call it hazard matrix, some people call it risk matrix, and frequency-based targets. exSILentia supports all three of these particular SIL selection methods. And we have, in exSILentia, we have a SIL selection tool called SILect. Those of you who've used exSILentia will be familiar with this. So if we look at the use of the risk graph, first of all, this is where we select categories for risk graph parameters. And bearing in mind what we do when we're looking at assessing risk and looking at hazards, we have what we call the three receptors. We look at personnel, we look at environmental, and we look at financial. And financial can be damage to assets, damage to reputation, lost business, etc., if you were to have an incident. And we always put personnel as the first priority because that's the most important. So when you look at a risk graph, you can see here, in this instance, we're looking at the personnel safety, but you could look at all three, and you have the ability to look at all three on the same graphs at the same time. So what we do here is we select the categories for the risk graph parameters, and we have a consequence parameter. Now, just to recap, risk, of course, is a combination of the likelihood and the consequence. How often is it going to happen, and what will happen if it does? And from the likelihood point of view here, we actually define occupancy. So what we're looking at is how often are people going to be in the danger zone. Then we look at what is the probability of avoiding the hazard. Will there be an opportunity if something occurs for them to get to safety? And what is the demand rate or frequency going to be? And so that's represented over here as occupancy is F, the likelihood, the consequence is C, the probability of avoiding is either PA or PB, and the demand is shown as W1 to W3. And these graphs will be calibrated according to your company's tolerable risk criteria. So if you don't know what your tolerable risk criteria is, it's going to be very difficult for you to be able to do this. So the way we do this is to follow the path determined by the selected parameters to identify the required SIL. So what does that mean? Well, we've talked here about consequence. And this is defined as the average number of fatalities likely to result from the hazard, which is determined by calculating the average numbers in the exposed area when the area is occupied, taking into account the vulnerability to the hazardous event. As we mentioned before, if they are exposed, if workers are exposed or the public's exposed, what would be the consequences of that exposure? From the occupancy point of view, what's the probability the exposed area is occupied? Again, that's determined by calculating the fraction of time the area is occupied. So if the area is going to be occupied for minimum amounts of time, especially if you're running batch, for example, if it's a batch process, it's not running continuously, it'll be running at various intervals, periods. And then how often do they need to be in there? Why do they need to be in there? Are they there for maintenance? Are they there as a result of a problem? And what's the probability of avoiding the hazard? And this is defined as the probability the exposed persons are able to avoid the hazard if the protection systems fail on demand. So obviously this depends on there being independent methods of alerting the people to the hazard and manual methods of preventing the hazard or methods of escape. So if they're there and something occurs, if there's an audible alarm or an audible and visual alarm, that they have enough time to get to safety and they have a means to get to safety. Then the demand rate is the number of times per year that the hazardous event would occur if no SIS was fitted. And of course, this can be determined by considering all the failures that can lead to one hazard and estimating the overall rate of occurrence. And this is based upon IEC 61511-3 Annex D. From the risk graph point of view, if we look at the parameter values here, we now, although we have qualitative, we actually managed to put some quantitative information in. So, for example, the demand rate, we're saying W1, it's very low, but we're saying that low, very low is less than once in 10 years. W2 is 1 to 10 years, and W3 is less than once per year. And then from the health and safety, so now we're back to our three receptors. There's the personnel, there's the environmental, here's the financial. And we've categorized minor injuries, severe injury, one death, several deaths, or many deaths, catastrophe. And one could argue that it's difficult to distinguish between several deaths and many deaths. And again, this depends upon how you define things in terms of your own acceptable risk criteria. And from the additional parameters where we're looking at the presence in the danger zone, we have seldom to frequently, which is defined as less than 0.1, or frequently to continuously. And then the probability to avert the hazard is under certain circumstances or almost impossible. So this is just an example. So let's say we have, from the risk graph, we have a SIF was identified during a HAZOP study. Safety department also determined that the probable loss of life, this is another term, PLL, probable loss of life, is 0.9. The area is normally occupied, and there is no possibility of avoiding the hazard. The demand rate is 0.05 per year. So what is the SIL? Well, again, if we look, PLL of 0.9, so we're looking at a CB, a severe injury or one death. The area is normally occupied, so again we're looking at an FB, frequently to continuous, and there is no possibility of avoiding the hazard, so this is almost impossible, so we're looking at a PB, so we've got an FB, a PB, and demand rate is 0.05 per year. So we're looking here at W1, very low. So if we plot that, we end up getting to a SIL1, as you see. CB, because we've said severe injury or one death, given by a PLL of 0.9. FB, meaning that it's frequently to continuously occupied. And PB, because it's almost impossible, there is no possibility of avoiding the hazard. And then our demand rate is 0.05, which is less than once in 10 years. So you can see it's a simple tool, and you can do that for personnel safety, then you can do it for environmental, and you can do it for assets. So the risk graph, and here's an example from exSILentia. This is how it looks in exSILentia. The demand rate is shown as W, and the probability of avoidance is shown as P. Same, personnel safety occupancy, safety consequence is C, occupancy is F. So here's our consequence, here's our demand or likelihood, and here is the ability to avoid or not, and of course the occupancy. And you've got environmental, and you've got asset consequences, so A. And as you can see here, we're looking at personnel in this instance. We always look at the personnel first because that's the highest and the one that we're concerned about the most. And then you look at the independent protection layers that you have in place currently that are non-SIS related. And generally speaking, as a rule of thumb, you would expect each layer of protection to provide you with at least a risk reduction factor of 10. That's the general rule of thumb. So if we look at the hazard matrix, here again, we've got to categorize the consequence. So we have here, we're showing 4 categories. The likelihood, we're showing here. and then you select the SIL from the matrix corresponding to the identified consequence and likelihood categories. Again, fairly simple, easy method, but this has to be calibrated according to your tolerable risk. So from the consequence considerations, clearly it identifies the basis of the categories, and you need to include considerations for injury, loss of life, property damage, loss production, environmental release. Again, our three receptors that we're most likely or we're always looking at, which is the personnel, the environmental, and the financial. But here again, it requires judgment or further analysis to assign these consequence categories. So you would have to do some quantitative risk assessments, and usually that's done further, much before this, and that helps drive what the tolerable risk criteria will be for the company. And like I've said before, it depends if the company is more risk averse or less risk averse. So if we look at an example again, a SIF was identified during a HAZOP study. The HAZOP team determined that in this case the dominant consequence is 1 death and the likelihood is once per 200 years. So again, what is the SIL? So if we look at this, a dominant consequence is 1 death. So we're looking at personnel, and we're looking at a single fatality, which means we're looking at a C3. And then the likelihood is once per 200 years. So we're looking at between 100 to 1,000 years, which is a D3. So we have a D3 and a C3. And if we follow that through, we see that we have a SIL1 requirement. And then you would do the same for environmental, and you do the same for asset. As you see, it's a simple tool that can be used, and it gets you into the area, the band that you're looking for. So in exSILentia, again, we have a hazard matrix, as you can see here. And there are, it gives you at least 7 categories. So you can expand, and you also can see here that you can have personnel, environmental, and assets. And it allows you to provide some customization too. So for example, you may say if there was to be an incident that was resulted in say multiple fatalities or even a single fatality, then there would be some impact to company reputation. There might be loss of business. There would be downtime because maybe the assets have been destroyed, etc., etc. And from the consequences point of view, same 3 receptors, as I've said before: personnel, environmental, and assets. And then you can look at independent protection layers. What do we have in there? There's independent protection layers. So then frequency-based targets. So the first 2 that we looked at, the risk matrix and the hazard matrix, were qualitative or qualitatively based. And sometimes they're known as semi-quantitative because you can define certain parameters. But ultimately what they do is they get you into a typical SIL band, a typical band of risk reduction. However, it's good for a first pass, but you want to really be more specific, because as you go up from a SIL1 to a SIL2 to a SIL3, the cost of number 1, designing that, and number 2, maintaining it throughout the life of the SIS is going to be significantly different, especially if you're looking at SIL3. So, and of course the bands get wider. The SIL1 is between 10 to 99. SIL2 is between 100 and 999, and SIL3 is 1,000 to 9,999. So what you want to do is you really want to be much more specific in the target risk reduction factor that you're looking for. And this is where frequency-based targets can come in. So you select the frequency target based upon, again, consequence, and then you calculate the required risk reduction, and you assign the SIL based on the required risk reduction. As I said before, from the process point of view, the majority of the SIFs will tend to be demand mode, low demand, and there is a direct correlation between the amount of risk reduction that you achieve to the probability of failure on demand as an average. And basically the PFD average is equal to 1 over the risk reduction factor. So here, frequency that is allowable for a hazard event depends upon the consequence. And here we've defined personnel safety again, environmental and asset. And we've actually separated the safety into fatalities and injuries. And as you can see here, we're moving from minor to extensive. But now at the bottom, we have what's our tolerable frequency per year for each of these. So how do we calculate it? Well, the required risk reduction is a function of the unmitigated accident frequency and the frequency target. So unmitigated event frequency is after you've taken into consideration the layers of protection you have, what is the residual amount of risk left at the end of that? And then you have to divide that by your target. So what's the frequency that's left over your target frequency, and that would then define the risk reduction factor for the SIF. Another way of looking at it is when you've taken into consideration your layers of protection, what is currently left over what is desired. So here we have an example. Let's say we would select our SIL based upon our risk reduction factor, and as I mentioned before, the risk reduction factor here correlates to the amount of or the actual SIL levels. And you can see here a risk reduction factor between 10 to 99 would be a SIL 1, 100 to 999 is a SIL 2, 1,000 to 9,999 is a SIL 3, and then SIL 4 beyond. So this is based upon the tables that specified in the S84 or the IEC 61511 or 61508. But in most cases, the selected SIL should give more risk reduction than required. So usually, for example, if we said we wanted a SIL 1 SIF and our target was to achieve a risk reduction factor of 35, what we would say, or what we would specify for the designers, is that we want a SIL 1 with a risk reduction factor of greater than 35. You may even want to give yourself a little bit of margin of safety, because as safety engineers we tend to want to be conservative, so you may say a risk reduction factor of greater than 50, for example. So let's have a look at this type of example. An accident scenario yielded a consequence of 0.21 probable loss of life and a likelihood of 1 in 57 incidents per year. What SIL should be selected? So again, here's our table. So we're saying our probable loss of life is 0.21. So clearly that's less than 1. So we can see we have 5 times 10 to the minus 4 as the target frequency, or the tolerable frequency. And then if we apply our equation, we now have 1 over 57 divided by 5 times 10 to the minus 4, which gives us a 35.1 risk reduction factor. So in order to achieve a 35.1, we should either specify SIL 2, or we would specify the risk reduction factor with the appropriate safety margin. So you can see if you were just to specify, okay, risk reduction factor 35.1, that's a SIL 1. If you just specify SIL 1, what you may end up with is that the designer could give you a SIL 1 SIF, but with a risk reduction factor of 10. So that doesn't achieve what you're looking for. So that's why you would say it would be a SIL 2 if you were just going by SIL bands, or you would specify a risk reduction factor greater than 35.1 with an appropriate safety margin. So here is an example from exSILentia with the frequency-based targets. We have the health and safety, again, environmental, assets, and then you have the user-defined and custom. So all of these can be calibrated against your tolerable risk criteria. Then you can look at the initiating event and frequency, any enabling conditions and probabilities, and what are the independent layers of protection. The effectiveness per receptor, any reuse, and particular IP or tags. So you can define all of that. So at this point, what I want to do is just the last few minutes is to show you an example from exSILentia. So we have our SILect tool. This is what we're looking at. If we look at our tools that we have available, we have the hazard matrix. If we click on our hazard matrix, we can see now we have our risk receptors, our personnel, environmental, and assets, and custom, and we have our matrix set up according to our tolerable risk criteria. So it's been calibrated, and we can see here we have the demand frequencies, how often is it going to occur, and then moving across, what are the consequences from the point of view of the three receptors. And that's what we're using here. So here we're saying our demand rate is 4 to 20 years. We will get a single fatality. The environmental impact is that there's a localized effect. And if you click on each of these, you can see we have 7 consequences that you have defined here. And if we said, all right, we were having a localized effect, what's the local damages? Again, you can define these, and this would be from the table. So we're saying we're looking at local damage of, say, 100,000 to 1 million, and is there a business impact? We're saying there is a business impact. And we could put on there financial cost of that. What are the independent layers of protection that we have? Well, we only have a relief valve, and as a result, if we would have this scenario, then our SIF would have to be designed to meet SIL 2. Again, personnel safety is the key one, and obviously we would take the highest requirement. And in this case, this is a SIL 2, or even though these are only SIL 1s. So therefore, our target is a SIL 2, based upon that configuration of the matrix. If we look at the risk graph, here's our risk graph again, as we saw before, and you'll see over here you can choose risk graph or hazard matrix. You can choose the frequency-based target. So we've chosen the risk graph, and these would be calibrated again. In this case, we're looking at the personnel, and you could look at each one in turn. And so, based on the hazard matrix, we come back to this. We had this already set up. We go to the risk graph. We have this already set up. And then if we go to frequency-based targets, you can see here we've defined for each of the receptors, personnel, environmental, and assets, we've put in the frequency. Now you can see we could also put in an associated cost per year for the asset loss and for the environmental. And then you can define for your customs side of things what you would consider to be further requirements. So all of those can be set up. And so it's very easy to use any one of these three to create or to use for a first pass. And the frequency-based targets obviously give you, if we go to, we're looking at the next one, which is silver. Let me get to it. Let's just move this out a little bit. Although it's not coming. Oops. We'll go to silver. So we have set up our target for our SIF, and then we would need to design our SIF to achieve the target that we're looking at. And you would use the silver tool to do that. So using exSILentia is very easy to do the SIL selection as long as you have defined your tolerable risk criteria and you've considered all your non-SIS related layers of protection. And then what you have left as your residual amount of risk reduction, you would then define as a target SIL. And the thing about the risk matrix and the hazard matrix is that they, although they're qualitative, they're a good first pass to get you into the ballpark. So if you know you're going to be looking at a SIL 1 or SIL 2, that's important. So that then you can start looking a bit further and say, okay, let's if it's a SIL 2, okay, are we looking at a high-end SIL 2? Are we looking at a low-end SIL 2? Are we looking at a mid-SIL 2? Where are we in that? And the other thing the dashboard can do on exSILentia is it can show you what your target is versus what you've achieved with your design. And you can see over here that you can select different life cycle stages to work on, and it all flows through. So if you start with the PHA, there is a new addition to the tool for LOPA. So you could actually, after the PHA, then you could look at what layers of protection you have in place, and then from the LOPA you will have residual amount of risk reduction that you need to achieve for each particular scenario, and then you would design a SIF based upon that amount of risk reduction required, whether it's a SIL 1, SIL 2, etc. So that's where the SILect comes in when you start looking at, okay, I need a SIL 1 or a SIL 2. So that, in a nutshell, is how you would use exSILentia to do the SIL selection. And what I will do now is, for the last 5 minutes or so, open it up for any questions. Let's see if we've got any questions yet. Okay. I see that there's some questions here. Let's have a look. Okay. There's a question here that, do you still need to manage a SIL 0? You know, that's an interesting one, because there is, according as per the standard, there is no SIL 0. Anything below a risk reduction factor of 10, you may decide that you will, instead of putting in a safety instrument function for that, you will probably go back and look and see, okay, what other layer of protection can I put in there? Or if it is actually coming out less than a SIL 1, you may say, well, okay, for the cost and the benefit, I should put in a low SIL 1. But there really isn't anything defined as a SIL 0. That's the thing to remember. Let's see if I can make this bigger. It's difficult to see that. Okay, any other questions? Anybody, any other questions? Okay, well, if there are no questions, hopefully you found this interesting. The next one we're going to do is, having done the SIL selection, is to do the SIL verification using exSILentia. And that'll be the subject of the next webinar. So it only remains for me to say thank you for attending. I hope you found this useful. Please refer to our website for any additional information. This is also recorded, this webinar, and it can be replayed at any time. I would like to mention that we do have some training coming up. There is an exSILentia course that is scheduled for, I believe it's the the week of the 9th of November and the 12th and 13th. And then the following week is the FSE 100 course that's been run at Warwick. So if any of you are interested in attending those, please register through the website, or if not, you can contact Ali Coles at ali.coles@exida.com, who shall be very happy to help you with that. In the meantime, if you have any further questions, feel free to email me at sgandy@exida.com, and I'll be happy to answer any questions you have. So with that, it just remains for me to say thank you again. Enjoy the rest of your day, and hope to see you on the next webinar. Thanks a lot. Bye now.